This is a short section, but it's really very important, and there's a lot of information in this little section. Our goal here is we're going to define the term buffer first. Then we're going to name two factors that determine the effectiveness of a buffer in solution. And then we're going to ask the question, at what pH are buffers most effective? Let's look at a buffer. First thing, if we're looking at a buffer, we're looking at a weak acid in solution with its salt. We want to start out by looking at this compound here. I've chosen the weak acid, acetic acid. It's got a dissociation constant of about 1 × 10⁻⁵. So if you throw this in the solution, only about 1 out of 100 of these molecules dissociates. That's in pure water. We're not going to be talking about pure water here. Now, we can get, if we put this into the Henderson-Hasselbalch equation, we know that the pKa is going to be about 5. And lo and behold, the pH, look at it, it's about 5 here. It's really a little bit less. It says pH equal pKa 7.6. This is in a solution when we have exactly half acetic acid and half acetate. That is, we threw the acetic acid in the solution, and then we adjusted the pH so that we have half acetate and half acetic acid. How did we do that? We put it in solution, it dissociated, and then we removed hydrogen ions, the point where we get to pH of 5. All right. Now at this pH, we're going to have exactly an equal amount of HA and A-. That's a little equal sign there. The way to read these charts, you've seen these charts before. The problem is sometimes they put the x-axis up here and the y-axis down here. But here's the way we're going to read this. An equivalent of OH added. Well, we're going to say we're going to start out with one equivalent total of acetic acid. That's acetic acid plus the acetate. The two of them are one equivalent. Now, if we add enough acid to this solution, if we add hydrochloric acid to this solution to lower the pH to 1, okay, this line here will come right down to here. It curves off and comes down to here. Okay. We can start out with 100% of the acetic acid in the form of acetic acid and virtually no acetate in solution. If we start to add equivalents of hydroxide, now remember when we add one equivalent of hydroxide, we're going to be over here and we're going to have removed every proton from acetic acid, and all we have left is acetate and protons. And that's how we go across this curve. And I might suggest that's what you do with every problem you have in this course, is turn whatever that amino acid or acetic acid or carbonic acid is into the acid form. Make it completely acid, and then to start dissociating it and work in that manner. I know you don't understand everything I'm saying right now, but it'll get to you in a little while. We'll cover it over and over again. Okay. Now, we're going to start in all the acid form here, acetic acid. We're going to start adding hydroxide, and look what happens to the pH as we add hydroxide. Now I'm going to tell you, if we were at pH 1, we'd be clear down here, and the first little bit of hydroxide we add is going to zoom us right up to there. There's no buffering capacity there at all. And if we didn't have the buffer in the solution and we added this much hydroxide, we'd already be at pH 14. We had gone through the whole pH scale from 1 to 14. But it won't happen because we have this buffering system here. We have a weak acid in equilibrium with its salt. So when we get up here within about 2 pH units of the pKa, we start to see buffer. We're no longer changing at this rate. The rate of change upon addition of any amount of hydroxide, if we add an even amounts of hydroxide ion across here, and we look to see the change, when we get here, this change here is going to be less than the change from there to there, And this change here is going to be less than that change. This change of pH here is going to be less than that change of pH. And that's going to happen until we get to the place where the pH equals the pKa. And after we pass that point, every time we add the same increment of hydroxide, we're going to get more of a change in pH. Now we say until we get to here, and if we add a little more hydroxide here, we're going straight up to 14. So there's a tremendous change here because you have no buffering capacity out here. And you have no buffering capacity down here. You only have the buffering capacity when the salt is in equilibrium with its acid. Remember, that's part of the statement. So the way you say, usually when you look at a biological buffer, carbonic acid is going to be an exception at the end of this chapter. We'll talk about that. When you look at a biological buffer, you usually say, where is it a buffer at? Well, it's a buffer in a certain pH range. What's that pH range? You find out what the pKa is, and you say plus or minus 1 pH unit. So if the pKa is 4.76, this will be a good buffer between 3.76 and 5.76. And 3.76 is right there. And 5.76 is right here. And you can see after you get through that range, from here to here, this is where when you add an acid in that direction, or if you add base and go in this direction, you don't change so much. The buffer resists change. How does it do that? Well, if you, down here, when you add hydroxide to this thing, every time you add a hydroxide, acetic acid dissociates and the hydrogen ion combines with hydroxide to make water. So essentially you add the hydroxide, but the hydroxide doesn't add base to the solution. It just combines with the acetic acid. And that's why you have this resistance to change. If you went in the other direction, you could do the same thing here and say, we start here and we're adding acid in that direction. As you add acid to this thing, the acid simply combines with the acetate and makes acetic acid. When that happens, the acid you added did not change the pH of the solution. It just changed the ratio of acetate to acetic acid. I want to back up here and go over this. This is the Henderson-Hasselbalch equation, which we said that you need to memorize. What this says here, we said that a buffer functioned best when it was at its pKa. Well, if the pH, this pH is equal to the pKa, then that means that this term has to be equal to 0. How do you make this term equal to 0? This has to be 1. How do you make this 1? You have the same concentration of salt of the acid as you do acid. That makes this term 1. The log of 1 is 0, and the pH is equal to the pKa. As you increase, if you add acid, the pH is going to drop. If you add acid to this buffer, it's going to combine with the salt of the acid and make more HA and less salt of the acid. So this term is going to get lower as the pH drops. If you add base to this solution, it's going to combine with the hydrogen in the HA and turn it into A. So this term's going to get smaller, this term's larger, and the pH is going to go up. Now, when you get several pH units away from the pKa, when the pH is several units away from the pKa, like at 3 or 7, you have all the salt of the acid or all the acid. So it's no longer a buffer. It won't resist changes to acid and buffer at that point. Acids and base at that point. In fact, in this region here, the pH changes very readily when you add acid or base, because this thing can't function as a buffer by itself. And that's essentially, you have all the acid in solution. when you have all the base in solution and you add acid or base, it can't function as a buffer, because you have to have both the salt of the acid and the acid in solution and together for it to be a buffer. And we say that usually within 1 pH unit, that is when the ratio of salt of the acid to acid is somewhere between 10 to 1 and 1 to 10. That's when it's going to function as a buffer, within 1 pH unit of the pKa. So, we want to get back to the question we asked at the beginning. We want to go back through this again. Define the term buffer. A buffer consists of a weak acid and its conjugate base in solution together, and they resist change in pH when an acid or a base is added. Name 2 factors that determine the effectiveness of a buffer. Well, one is what pH you're at, because if you're talking pH 12, if you're up here, this is not a buffer for pH 12. This is not a buffer for pH 7. This is a buffer, because of its pKa, this is a buffer for right around pH 5. So you have to have the right buffer. You have to say, what's the pH of the solution I want to buffer? Well, in biology, it's usually, not always, but usually somewhere between 6.9, which is the pH inside some cells, to 7.7 or something like that, which could be the pH of blood at certain times. Most of the rest of the time, that's where you really want your buffers to work. Now the urine, though, you're talking somewhere between a pH of 4 and a pH of 8. So buffers there, you get quite a change you got more latitude in choosing a buffer for that. And then if you talk about your stomach where the pH is 1 or 2, then you're talking about another set of buffers if you want a buffer. So you have to know what the pH of the solution is to choose a buffer for it. Okay. So what are the two? What's the answer? You still don't have the answer to name 2 factors that determine the effectiveness of a buffer. One is the pH of the solution and the pKa of the buffer. The second one is, let me ask you this. If I have 1 molecule of the salt of the acid and 1 molecule of the acid, is that going to be a buffer? No, because it's like having nothing. So the concentration, this question, a lot of students don't get this. You need to think about it. It's so simple, but you don't get it. I mean, some people don't. You got to have enough buffer there. Phosphate's a wonderful buffer at pH 5, but if there's no phosphate there, it can't be a buffer. So if you're talking about outside the cells at a pH of, for some reason at a pH of 5 or 6, phosphate could be a good buffer if it's there. If you're talking about inside of a cell, well, you got lots of phosphate there. So you've got to have enough of the buffer. That's why we pointed out at the beginning of this class, in the blood, carbonic acid is an important buffer. So is hemoglobin. But inside the cell, inside the tissues, except for the blood, it's not a good buffer because it's not there. You have to have the concentration and you have to have the proper pKa for the pH. And then you have an effective buffer. Okay, I guess we've run that into the ground.